Hello, this is Physics 2211, and this is our third lab, black hole and its orbits, and my name is Barry Moody. So the purpose of this lab, the lab was divided into two parts. The first part was we analyzed the motion of a star around a black hole, and then using that analysis, we determined the average mass for the black hole. And the second part of our lab was to take a ship that had landed on a moon and determine its exit velocity from the moon in order to get a figure-8 orbit around the planet in both the moon and the planet. So the fundamental principles of this lab were Newton's second law as well as the law of universal gravitation. Both these principles were used to determine the net forces on these objects, and then these were important to determine the perpendicular and parallel forces as well as position update formulas and where these objects would be located. So this is our glow script for the black hole. And the big things we changed were first we started with p hat, where we first talked about the normal vector and determining the change in momentum. And then we figured out the parallel components and the perpendicular components to figure out where the star would be moving. And then using that, we were able to determine the mass of the black hole. Our results were achieved by using the universal law of gravitation, which is then used to figure out the mass of the black hole. And since a lot of the numbers on there were changing, such as the radius between the star and the black hole, we received a plethora of different data values, mostly ranging from numbers from like 1.7 times 10 to the 17th all the way up to the 19th. And our average mass of the black hole was 1.33 times 10 to the 18th kilograms. Next, in our glow script for the figure 8 orbit, the biggest things we changed were here in line 67 and 68, we estimated and just kind of plugged and chugged a bunch of different values for the ship to find when they would get a figure 8 orbit. And the biggest things we changed were the distance to the moon. We figured that out would be, the moon position minus the planet position. And we figured out the net force on the moon based off of that, as well as we did the same exact thing for the ship in order to determine how these properties would move in with one another around this planet. Then we had the moon velocity update formula and the moon position update formula, and similarly for the ship, we had the ship velocity update formula and the ship position formula. After trying many different velocities, this is one of the ones I got closest to, orbiting both the planet and the moon. And as it takes off, it sort of oscillates around the moon and the planet system. In other observations, many were able to go around the moon and they often got stuck around the planet and even times almost escaped the whole system entirely but was brought back slowly into the planet system. What does it mean? And in part one, the rate of change of momentum is different from the parallel and perpendicular forces. Why is this? But it is due to the approximation of the mass of the black hole. So when we were determining the change in net force, this was based off of our net force from the distance between the black hole and the planet. And since we're estimating the mass based off of this, we get a bunch of different values based on the changing radius. And because we're getting a bunch of different values, we get different net forces, which lead to somewhat of a slightly the data being slightly off and why we're getting a range of values compared to one singular value. And that goes into why we're getting a different rate of change of momentum rather than the parallel perpendicular forces combined. Lastly, for a what if question, if our imaginary system had a black hole, a star, a planet, and a moon, what will we need to include in our computational model to show predicted motion? So in similar to what we did in part two, we would have to include the net forces on all objects in order to predict the motion and the position of these objects. And the most dominant force on these objects would be the black hole, simply due to its sheer mass being large scale. It would be the most prevalent force present, depending on how close the black hole is, and leading to the biggest component of the force on the planet, the moon, and the ship.